start with a few images just to remind you the context that we are using for our research, which is in the field of neuroscience and psychology called embodied cognition, which is really the grounding of language into actual perception, which is also the theme of this topic. So these are examples of images that remind us about language learning. So the GABA guy or rabbit is a language learning example for those that know about psychology and philosophy. So if I hear GABA guy in front of a rabbit in a new community with a new language, how do I know if GABA guy means rabbit, it means eyes, it means animal, or anything? The example of gestures and also finger counting is used a lot as an actual component in the learning of abstract concepts. So it's relatively easy to learn that if I have a rabbit, I touch the rabbit, I see the rabbit, I will call it rabbit. But what if I have to call or name something 1 or 2 or 3? So one rabbit is 1 apple is 1. How do we get to work out something else? So we know from, again, psychology and neuroscience that this is important. And then you will see other evidence there. This is work done by a colleague of mine in Plymouth, a psychologist, Rob, who does work on visual and action without language initially. So you have affordance given by the shape and the features of the objects. So you have affordance for the manipulation, particularly the hand directions. And this affects the way we process visual objects. And another example from neuroscience of the link between action and language is the demonstration by Friedman Pulver-Muller that if you visualize the brain of people performing a pure linguistic task, which is deciding if the word that you see, cake, click, or click, is a word in the dictionary or not, yes or no, the mental representation of the meaning of words, which is the action of clicking or licking, is actually present when you are not supposed to think about the meaning. You are only telling me a dictionary linguistic lexical revision task. So further evidence, plus an explanation of the neural mechanism behind it. And this is the work that I mentioned by my colleague Rob, together with another colleague, Jeremy Gosling, with whom we have done also work on EEG. And in particular here you show that even for those familiar with EEG signals, in the first 100 milliseconds, which pre up well before we start to plan and execute the action, so it's really a visual component, the modulation of the visual signal is actually affected by the affordance of the object. The affordance in this case is size, power, or precision grasp, or left and right if you use different signals. So vision is actually affected before language and before you start to execute the action already with a motor component. Quite a stronger result. So this is the technical background. In addition, we do developmental robotics, which is we model learning and stages of development in robots. And therefore, we have looked with a colleague, Schlesinger, at the literature on language in language learning. And one or two of the main phenomena in language learning is embodiment. That is the involvement of the child's body in the learning task. And you will see specific details because it's the focus on my talk, really. How you model child's language learning stages into the robot. Language, in my sense, is always semantic, action-based, visual-based representation of words. We don't do just Siri or Eliza type symbol manipulations. So the field in which we place our approach is called developmental robotics. We call it developmental psychology, child psychology, so let's call it child psychology. And of course, as you've seen already from the start of my talk, there is a strong psychology and neuroscience component. Clearly, you need the expertise from the roboticists to provide the robot platforms, AI or computer science to provide machine learning techniques and so on. Having given this introduction, I'm going to focus on 2 or 3 sets of experiments depending on time. The first one will be a few examples of language learning, embodied language learning, which means learning names of objects that you see, and names of objects and actions that you perform as a robot, as a humanoid robot. We use the humanoid icon in most of these examples. So let's start with one theoretical element in child psychology, which is the demonstration by Linda Smith that children use their posture, so their physical interaction with the world, to help them learn the meaning of words, even when the objects are not there. Because classically, you hear the word, you see the object, gabaga, rabbit, you see the rabbit, and you make the association. Children can use their body as a memory of the interaction to learn that there is a rabbit, even when the rabbit is not there anymore, if the embodiment posture relationship is still there. This is called body as a cognitive hub the idea is that in the early stage of a child development, and we copy this in robots, you have embodiment or physical interaction as a hub, central hub, to connect your modalities, vision, speech, action, execution, and so on. And to demonstrate this, you're going to see a movie from a psychologist there. This is the classical paradigm. It's called the MODI setup, where you show two objects on two different parts. So the child there, you see the hands, has to physically engage in a left versus right attentional mechanism, of course, grounded. At some point, she's going to hide the two objects, and then she's going to name for the first time the object. The new word that she uses, not gavagai, like in one example, it's MODI, just a new word. This is work done by Linda Smith and collaborators at Indiana Developmental.
Look, it's a MODI.
So the research is naming the object when the object is not seen. In new experiments, they don't even use this bucket. They just point at space where the object was. Make sure that the child again engages physically in the two conditions, and then after, she's going to test the knowledge of the child. So can you find me the MODI? So the typical setup is left and right, hide the object, name it, let them play again, and then mix them and test them. Of course, to make sure, and in this case 73, which is about chances for psychologists, these are 1.5-year-old children, which sometimes takes days and days of presentation to learn a new word. In this case, they are trying, it's called the fast mapping, learning in a single presentation. So you do this, and this confirms the effect, to make sure as a good psychologist that it's not due to something else. You select the position at the beginning, so 50% chance of each object being in the two sides. And of course, you get a chance for a chance level of the child. These and other conditions demonstrate that this is the mechanism working. So what we did, we started to use some of these embodiment mechanisms. Not only this one, there is something else called mutual exclusivity. When you have many objects, and you know the name of all objects but one, the child has the hypothesis that by mutual exclusivity, the new name must be from the new object. So all these are put together into a series of experiments, and the learning architecture that we use was developed by my collaborator, Tony Morse. This is part of the ITO project results. And it uses primarily two mechanisms: code and self-organizing maps to pre-classify features, visual features, color features, shape features, and so on. Plus you have pre-processing of speech signal, I guess that we have speech recognition from the individual word. And in addition to these code and maps, you have Hebbian learning to learn associations between the modalities. So it's very simple, but you will see it, although I'm not showing that movie integrating all these, actually all these mechanisms can be implemented in the same architecture. And Tony,
so this is the ICO robot.
Tell us how this experiment works.
Some objects. A truck and a ball. So let's see how we go.
The first example is called the fast mapping. You show the object, you say the name when the object is inside. And then you do the testing. We don't get to manipulation here yet. This is more posture-based embodiment. In the next experiment I'm going to present, you get more engaged active manipulation of the object. The key element in the cognitive architecture is the coded map representing the state of the robot in terms of postures. So left and right is a different state within the coded map. And that's the MODI setup.
So when children learn the names of objects, those objects don't have to be in sight. It can be through association. So we'll show you how that works in the robot. So we'll show you the object.
What you see there is motion filtering, set map for motion, just to decide the focus of attention.
And you hide the object.
So you hide the object.
Yeah.
You make sure the robot is looking in the right direction, you say the word, and you do the testing, and trust us, the results are there, and these are the charts demonstrating in gray to the child data, in the blue data, and in the robotics data, to see that in the different conditions, you only saw the details of the first two, you get the performance. Plus, although I have no time to discuss this in detail, we use the robot to make prediction on the mechanisms used by the children for language learning. Because in the child, the robot, you can change the posture. So you can let the robot sit or stand up. We actually raise and lower the table. So if you change posture by a big amount in terms of posture of the robot, you might lose the effect. At the same time, using two different meta postures, up and sitting, standing and sitting, in addition to left and right, you can actually learn two tasks. This is what our iCap did, and this is what the children in the States lab demonstrated they can do. So it's a nice two-way interaction with the technology. But this is one first approach to using posture as an example of embodiment for language learning as a strategy. A slightly different approach is the one used by my PhD student now, who's just finished, Martin Pena. In this case, the architecture is different because we model in the artificial neural network the individual steps of the actions. So you don't have a final posture, you have the continuous control of the robot elements. And we use 9 objects and 9 actions, if you will see some examples in the next movie, to test the capability of the robot to make the association between different objects and different actions, including generalizations, which is if I learn to use one action, let's say lift, with 8 objects, and then I name the 9th object, the robot is able to learn, like we would do in language, to generalize the use of the object for the same action, which is the cooperative architecture is a NPRMN, which is a time recurrent neural network used by Giuntani. I'm afraid I don't have time to look at the technical details, but this has been published. What you see here is the test. Sometimes there is a bit of a delay when I switch between movies, lower the size of the movie here, but I tested and it started to work as well.
Touch the ball.
So here, every single movement of the robot is controlled by the output of this artificial neural network. This highly dynamic recurrent neural network. And what you see here are generalization testing. In the sense that the robot was never tested.
Slide left, the ball.
Was never trained to touch a specific ball, was trained to touch other objects. So this work was presented actually 2 days ago at IUCN in Beijing.
Slide right, the ball.
So much time have I got? Because I have this, I'm going to really, unfortunately I already speak too fast. Plus the time pressure adds to this. I'm going just to mention.
Problems including questions.
So I'm just going to mention the set of experiments and looked at the way you can use the robot to learn abstract concepts like numbers. And sorry for really just the snapshots presentation of this case. So we use an example in which we demonstrate, these are child data, that will allow the robot, for the child, to point at objects being counted by the voice, by a researcher. You get an increased performance in the set that you can count, the size of the number you can count. And we use the same mechanism with a learning model, another neural network, where the robot is asked to do the pointing. And the pointing helps the neural network to basically learn a bigger size, a larger set size. In addition, we've done, this is recently published, January 14, we've done work on using finger counting as a strategy to count. And what we show here is that if you teach the robot to repeat sequences of numbers just verbally, 1, 2, 3, 4, without finger counting, you get a representation of numbers. If the robot can learn this, the network can do this. Or you get a representation of numbers, which is really mixed. This is the cluster analysis of the internal layer, or the hidden layer. If instead you teach the robot to repeat the sequence whilst it's repeating the physical action, which is the finger counting, you get an organization of the representation of numbers, which is numerically relevant. 1 and 2 have a distance of 1, 9 and 10 have a distance of 1, while here you see 10 and 9 are totally different. So by helping the robot to count with your fingers, you help the robot to really represent numbers as a continuum, and this network, without the need of extra training, can also do additions. In the sense that you say 1, the robot activates 1, including doing the 1, and then you keep the activation. You say 2, the robot then activates 2, adds to 1, and the result will be the physical combination of these distances, which are distances with the physical. And now, 5 minutes probably, to present the work that Caterina passed from the coordinator of Poeticon and Yanni Alimos from Maryland, who sent me, this is part of the Poeticon project. We haven't yet collaborated on this, but this is work ongoing. So we thought I would present this because you will see this is exactly on adding manipulation, vision. I haven't talked much about vision, to be honest, because we use standard visual tricks, color filtering and so on. Here you will see a more advanced application of vision routines with language representation and robotic implementation. So I'll skip this. The first work that Yannis has done Yannis Animanos did as part of this project, together with other colleagues, is to have an automatic object monitoring system doing filtering, tracking and segmentation at the same time using specific techniques, is to identify 6 motor primitive goals, because in this case actions are defined as goal. So the 6 that he identifies that we shouldn't say universal, but these basic components that can explain all possible combinations are actions like the form. So in this case, you have 2 objects, and one of the 2 objects is the form, change the shape. You have transfer, you see, you switch the object. He has done a systematic arrangement of this. And I'm going to show you a movie, a video of this being used in action. This is to apply the divide goal, or primitive goal, let's say. And also there is a transfer. We do work in this project on cooking-like tasks, food preparation, which is also here, so it's related. So you do transfer, and you see that there is a way to, by using the 6 goals, to be able to track the elements. So this is work done by Yannis as the expert in vision in the team. In addition, Yannis and Caterina have done some work on using the minimalist representation of grammar, a Chomsky representation of language, applied to actual representation, goal-based actual representation. So if you remember, for those familiar with linguistics, you have a sentence, noun, and verb predicate, and then you can decompose it into noun, article, and so on. Here, this is all done based on actions and goals. So tighten with right hand, with wing nut and so on. It can be decomposed into a series of goals, which is tighten, and then a series of subdivisions of words, like in a grammar tree. And what we do, actually what they do, is they put all things together. The 6 goal identification vision system with the grammar, they are combining something called praxicon. The lexicon is a dictionary, it's a list of words and the meanings. The praxicon is a definition of actions according to their goal, and of course a series of tree-based representation that links things together. So what we see here, that every time there is an action being monitored by this goal-based identification system, you start to generate add trees or sub-trees in your representation, which is the full representation of the task. So the first goal, I think, was, I'm not sure if this is the first. The task is to probably nail the nail on the plank. And of course, to do this, you need to decompose this into a series of sub-actions. And this is what the system does. By creating first, you need to grip the handle of the hammer, I guess. And then you have to move the grip with right hand the nail, reach with nail the plank. This is a decomposition. And this is done automatically by the Praxicon system. And I understand that the Praxicon is being released open source, and is a component of it in the near future. Okay. I managed to present the work, which was very important, and you will see more examples of how we can use additional vision routines from affordance, I guess, from the talk by the people in Lisbon. And also Giorgio Metta and Salvini are going to present work related to it. It's by chance that there is this presence here, but it makes sense because of the topic. Okay, I think I can summarize and then leave some time for questions. So, what kind of message I hope you will remember in a few weeks about this talk? One is that it was all about, we call it embodiment, or if you want, vision for language and manipulation. The link between higher level cognitive representations, like number, reasoning, numerical cognition, or just pure linguistic cognition, with the motor and visual components. So our approach allows us to do this, and in particular from a theoretical point of view, which goes back to the psychologist. We have proposed this body as a cognitive hub hypothesis, as an early developmental strategy that helps the child to integrate many modalities, vision, action, together. As a child, you will be bombarded almost by all these stimuli, multimodal stimuli. How do you integrate? How do you sort them? So body helps you to structure the task into, I put something on my left, something on my right, and this simplifies, let's say, your memory load. You see that this system is relatively powerful because you can go from simple tasks like naming an action that you perform or an object that you see, with naming objects that you don't see, or naming concepts like numbers, which you don't see in a straightforward or systematic way. And another important aspect in our field of research is that we can do a two-way collaboration with the neuroscientists and psychologists. In addition to the work that I mentioned here with the baby lab in Indiana, we are now collaborating with Friedman Müller, who is now in Berlin, who is the neuroscientist of language who does the experiments. In that case, we are using still the ICAP for robotics, but we implement our neural network on Spinnaker, Steve Ferber's new neuromorphic system using spiking. That's a slightly different direction, and we try to model cortical areas in the brain involved in motor representation, vision representations. Of course, we have achieved relatively simple robotic tasks. There is a lot to do. In particular, one important aspect in our developmental approach is the idea of cumulative learning. We want the same robot to add number learning, object naming, action naming. Here I presented almost three totally different architectures to do three different tasks. What we would like to have is a modular architecture that integrates and cumulates. This is the main challenge. Plus, of course, the implementation aspects. And I think I can stop here, acknowledging the collaborators who have done the work and the funders, and also giving you ideas for a Christmas present. In December, our developmental robotics book, co-written with Matthew Schlesinger, will be published, I promise. I'm correcting the proofs, so it's real. So if you need an idea for your Christmas present to your students or to your supervisors, buy it. Thank you.
We have a couple of minutes for questions. Questions from the audience?
I have a question regarding when you talk about embodiment and how the body relates to the actions and so to the learning. I can see how the physical action gets represented in the network that then relates concepts together, but I don't see how the body makes a difference. For example, if it wasn't the ICAP that you were using, if it was a different humanoid robot or any other kind of machine that had a left and a right, would you get similar results? Is the actual physical body necessary? Or is the...
There are two answers. The first one is that the body matters in general because, as I demonstrated in the finger count, if you add a body, some body, it doesn't have to be fingers, it could be your 6 legs in an octopus robot. Then this helps you because in the body you are constrained to the sequence or the distance is a constraint that is there that you exploit for abstract concepts. Second part is why the ICAP, or is the humanoid body really important or not? I don't think we want to demonstrate that it must be humanoid. It could be an animal that learns to count with different legs, for example. What matters is that you your cognitive exploitation goes beyond a pure linguistic representation. So in language, I could look at language, use trees, just a pure linguistic element. I can do latent semantic analysis or Google typing or the numerical analysis of the distance between things, but then you don't get the semantic aspects and you don't get this. So somebody constrains you and helps you in some cases to learn concepts which are easy, names of objects, are also harder numbers.
The same example about learning the counting is really impressive. I was wondering the importance not only of the body posture, but things like the sequence, the numbers occur in the same sequence in the experience of the agent. So if there's association that this is likely to be the next thing, or is that also playing a role?
Yes, plus it's related to your physical constraints. Yeah. And the byproduct of this is that then you can actually use the relative distance, motor distance between your actions as a way, as I mentioned too quickly, I'm afraid, for doing simple operation like partitions.
Yeah, I'd like to ask you more about that, but I think
it's in the paper. Frontiers is a open access.
One last question, possibly? Otherwise, we can obviously carry on asking questions in the coffee break. Yes,
thank you.
Thank you very much, Angelo.